So um, I would just like to start with motivation. My lab on effective intelligence and robotics focuses a lot on sensing and using nonverbal social signals. And motivation for this really comes from human-human interaction. When two parties interact, we have the receiving end and the sending end of these signals. And these signals can be many things, including, how we orient ourselves, the distances we have with the respect to the person we are interacting with, our appearance, the way we use our voice, our face, our body. All of these actually help on the receiver end to form impressions, to understand or interpret our emotions and expressions, whether we are lying or being truthful, whether they can trust us, whether they can, like we can persuade them and so on. So there's a lot of functions that these nonverbal social signals have. But when we replace either the receiving end or the sender end with an agent or a robot, there are many questions, open research questions that still need to be investigated. And my lab focuses on some of these aspects. Today, I'll be trying to give you some example projects from my lab. But before we start, I just also want to bring us all on the same page because we might be coming from different backgrounds. So when I say creating artificial socio-emotional intelligence for robots, what I mean is these steps to be achieved. For instance, we start definitely with sensing users, and ideally we try to do this in a multimodal manner. So using different senses like cameras, microphones, or even physiological signals. And then we also need to rely a lot on background research. So social sciences, psychology, theories from there in terms of personality, expressions, emotions, and so on. And we rely on data. So we either need to acquire our own data or use data sets with annotations. And then we might need to do feature extraction and learning. If it's deep learning, obviously these two things can be done simultaneously nowadays. And then we need to evaluate our model as well. So once we can predict whether the person is smiling or not, this is not sufficient though. We can't stop there. What's important is to understand context as much as possible. And context actually is a very complex thing. It's difficult to model because it requires answering and responding to a big W5 plus questions such as who the person is, are they male, female, if possible, do we know their age, what their task is, where they are, the environment, and so on. So there are many questions. The more we can answer those questions, the more we can have an understanding of the context, and then we can actually do this interpretation in a context-sensitive manner. So for instance, then we can say the person is smiling, but this is the smile of happiness, or it is the smile of embarrassment. And once we have this interpretation, then on the system side, ideally, we should do context-sensitive responding. So it could be a robot, an agent, or even a system like a VR system. So with this in mind, obviously with this, I'm simplifying some of the aspects. I'm not covering reinforcement learning or other aspects related to continual learning. So I'm just sort of looking at it as a closed loop interaction with a sort of simplified manner with basic components. So then I would like to give some examples of projects we conducted in my group to achieve some of these aspects. So the first one I'll be talking about is called Investigating Taste Liking with a Humanoid Robot Facilitator. So this was mainly done by Zoni, and it was a best paper finalist at IEEE Roma 2020. So the motivation for this work really comes from humanoid social robots more and more sort of tested or being used for service industry. And particularly our vision in this research area is to try to sort of create autonomous service robots that have embodied multimodal interaction capabilities and that can also adapt and personalize to different users. And our approach initially is to actually look at human versus robot facilitation to understand similarities and differences and analyze different signals, but particularly facial expressions, and then focus also on deep learning, with the ultimate goal of creating really these autonomous adaptive service robots that can be used in various industries like restaurant settings, hotels, and so on. So starting with these facial reactions to taste, because that's something that is not as common as compared to facial expressions, it really is based on the research and idea that we can read from people's faces their appreciation and dislike of food and flavors, because these food and flavors cause corresponding facial reactions. And in particular, if these reactions are negative, they are found to be more quickly occurring than positive ones, both in adults and children. So there's a lot of research in this area now. The research questions we wanted to answer in this study was whether and how people alter their taste liking behavior and facial responses when they encounter various tastes, and whether these behaviors differ when the facilitator for tasting is a human or humanoid social robot. And in terms of contributions, this is really the first study that investigated how a robot facilitator can influence people's taste liking and their interaction experience. And also, we wanted to inform future social robot design with the service robots in mind. So we considered 3 independent variables in our study. So it's flavor, sour, sweet, bitter, spicy, and salty. And then facilitation style is either priming or non-priming, which means we tell the person in advance whether they're going to be now tasting a sweet drink, or we don't tell them and then just tell them to taste this drink. And then facilitator is either being a human or a humanoid social robot. So this leads to a fractional factorial experimental design with 27 participants, and we had 9 males and 18 females. And in the figure, you sort of see how they were tasting it. In terms of data collection, we collected 3 kinds of data. So we have the questionnaire data, also looking at participants' demographics, gathered data in terms of self-reported taste liking after they tasted each flavor, and also their interaction experience. We also collected video data from frontal cameras. And finally, we did a semi-structured interview just to gather some opinions and reflections and qualitative comments. So the first thing was doing ordinal logistic regression. So with that, we found that the 5 flavors can elicit different liking levels. And we see that in the first box plot. And we also found that taste liking was not influenced by a facilitator and facilitation style. So it didn't matter if the facilitator was a robot or a human. And then to conduct facial reaction analysis, we focused on facial action units. So we also used actually an available toolbox called OpenFace to automatically detect AU intensity and presence. An action unit means specific muscle movements on the face, like you see here, AU1 being inner brow raiser, AU9 sort of nose wrinkler, and so on. So we used the existing toolbox to do this, and then we did one-tailed man-Whitney U test, and we found that some AUs have significant difference in presence. So particularly they're more frequent in disliked videos, and these are AUs such as 1, 2, and 4. And some AUs have significant difference in intensity, and they're more intense in disliked videos. These are like AU6 and AU20. And in terms of interaction experience, what we found is that the facilitator type had no significant influence on interaction experience. So it didn't matter if it was a human or a humanoid robot. But the non-priming facilitation style had a significant negative influence on participants' experience in robot facilitator condition. So what this means is that when it was the robot that was facilitating, actually the participants wanted the robot to say what type of taste they were going to taste next, whether it's a sweet and salty one, rather than the robot just telling them to taste the drink. And then from semi-structured interviews, there were interesting quotes, but mainly related to, for instance, repetitive and predictive robot behavior. So one of the participants said, it was fine, but not so flexible. So they were more willing to express their opinions when they were interacting with a human. In terms of obeying facilitator, one of the participants said they knew they should only respond to the robot's instructions to indicate they were done. So they would not ask questions or check with the robot. And in terms of likability, one participant said they found the robot to be cute, and interacting with it made that person happier. So with this, I'm going to move to the second part. We have also suggestions for design, but I will not be able to cover in the limited time. So the second part of our work now focused on automatic analysis of facilitated taste liking. So I already sort of presented the aim, but here, particularly trying to automate the process, the aim is really to create an objective and non-invasive way of measuring and analyzing people's liking of the taste of flavors of different products or drinks. So it builds on the data set that I just presented. And really the idea is to ultimately include this in robots. So here we see more examples of the data set. So we call it the beverage tasting data set. So we have all this information. And what we got at the end is we have around 172 clips for disliking, 140 clips for neutral, and 65 clips of liking. So this is based on self-reports. And then we looked at both engineered features and deep learned features. So for engineered features, we use geometric features like you see on the right-hand side. So really detecting and tracking the landmarks and also looking at position, velocity, acceleration. But also we looked at appearance features such as HOG combined with PCA, and also higher level features, mainly action units that I sort of presented previously. And for deep networks, we looked at 3D convolutional neural networks with different variations. So either using raw video frames or detecting the facial region and just using those, or looking at specific feature regions such as eye and mouth regions as being more relevant. And then we also created what we call personality aware network because we had the self-reported personality of the people. So we created this F-region CNN personality networks with variations. And in terms of results, what we see, and there are many numbers, but I will just summarize. In terms of engineered features, we looked at these different 4 models, and we found that the AU-based model really performed best. And these like related facial expressions actually have better classification results compared to neutral or liking. And in terms of 3D CNN, what we see is particularly, so and that's in the second table, actually trying to include personality information, what we call personality aware network, really helps with improving the classification results. So fusing their personality information with facial features improves both models' performance. So here we have results such as F1 score being 90% or 90.86%. So based on this, what we conclude is actually developing robot facilitators. We call facilitator in a generic manner, could be waiters or, depending on what sort of role they can play in hospitality industry. It is actually a possibility and we can endow them with automatic taste liking capabilities. And deep spatiotemporal architectures actually are more promising as compared to engineered features. And incorporating the personality information of the human users really helps, improves the taste liking recognition, which means actually it can also be used for adaptation as well. So the second work I want to focus on and present is called Learning Social Appropriateness, of Robot Actions. So this was a collaborative work with Sinan Kalkan, who was visiting my group during 2020 as part of his sabbatical, and Jonas is the main author and the person who conducted some of these studies. So we wanted to focus on social appropriateness of domestic actions. So appropriate social behavior actually is not trivial, even for humans, but we still have an ability to recognize different social contexts. And then also we continuously learn from our observations. And in this work, we wanted to try to achieve this for, domestic robots, because in the future, we envisage these robots to become part of our lives, let's say in our homes, but even offices, and they need to be able to understand what is socially appropriate or not, particularly in terms of actions. And the motivation for the work also comes again from social sciences, in particular here, for instance, looking at distances and how we have certain distances considered as private zone, which is also like the intimate zone, and then gradually moving from there, we have this casual personal zone, and finally public zone. So depending on the distance, certain things would be more appropriate, but not only with the distance, also our relationships. So the closer we are to a certain person, it might be more acceptable for them to be our intimate zone. But if it's someone we do not know, then probably further distances are more appropriate. Also, we use Adam Camden's characterization of the F formation system for spatial organization as a conceptual lens to analyze social interactions. So F formations have been used in computer vision to detect particularly freestanding conversational groups. And there are various formations as identified by Adam Camden. So using these as inspiration, we created a synthetic data set, and we had these features, various features that we could vary to be able to have sort of different combination of these aspects and parameters. So for instance, we have a robot, whether we have a robot or not in the scene, and then we have a certain number of people, we can vary that as well. We can also decide whether there's a group and how many people are in the group. We can identify or decide the distances. So the distance, for instance, of the robot to the closest human or to the group, whether there's an animal in the scene, whether there are children in the scene, and so on. So that's the main motivation for creating a synthetic data set, because trying to have such variation in the real world with actual people, animals and robots would have been quite difficult. So this enabled us then to create scenes like this in Unity. And here you see a bit more in detail, just for demonstration purposes, particularly the living room environment, because it's much more challenging than considering, for instance, bedroom or bathroom in a home setting. So the living room environment really is the social space as well. So we can see how we can actually indicate whether the music is playing, whether there's an animal, and the robot operates around a circle or in the direction of an arrow. So that way, we created 1,000 scenes, and then these were with 16 robot actions. So they're actually mainly 8 actions with some variations for within a circle or in the direction of an arrow. And these include typical ones in home settings like vacuum cleaning, mopping the floor, carrying objects, brings food, cleaning, starting a conversation, and so on. And the next step was to obtain annotation for these scenes. So here's how it was done. So we used crowdsourcing, and each image was annotated by 15 labelers. And we also had some honeypot questions to ensure actually that we could filter, if necessary, the spurious annotations. So we asked them what they see in the scene. And then we asked them for each of these actions to actually indicate the appropriateness level. So from very inappropriate to very appropriate. We also asked them to provide reasons for this particular annotation. And then we did lots of different analysis. Here I'm just going to present a few of them. So based on the labels we gathered, we can, for instance, analyze how appropriateness labels provided were with respect to distance. So for instance, we can see that starting conversation is the most appropriate action when the distance from the robot to the closest human is around between 3 and 3.5. But as sort of the distance, sorry, it's the other way, I'm confusing. It's in the intimate zone, so 0.4. We are looking at the x-axis. And as the robot goes away from the human, so if you sort of gradually follow from that 0.4 area all the way to sort of 5.4, starting a conversation becomes less appropriate. And this is sort of opposite for things like mopping the floor or vacuum cleaning, carrying big objects. So these are really inappropriate when the robot is very close to the human being. And as they sort of move away from the human being, they become more appropriate. So in the public space, for instance. Another analysis is appropriateness with respect to orientation. So again, here we see variations, but also we provide underneath the facing directions between robot and closest human. So what is interesting, for instance, is starting conversation is really most appropriate when both human and robot are facing one another. So if the human is behind the robot, it is still very appropriate. But if the robot is behind the human, actually the appropriateness drops. So people do not want the robot to approach from behind and trying to start conversation. Obviously, when they're not facing one another, it's not appropriate. And other sort of appropriateness levels are again changing depending on when they're facing each other. So if they're not facing one another, things like mopping the floor, vacuum cleaning, and so on are appropriate. If they're obviously facing one another, they become less appropriate, and so on. And here are some visual examples. So this is very extreme case. The robot is alone in the living room, so there is no one around, and therefore what is provided as label by the annotators is almost all of the things are appropriate. Perhaps carrying food is not as appropriate because there's no one around, but everything else seems quite appropriate. Oh, I think I missed one slide here. Sorry. So then we actually did some continual learning because we wanted to, in a way, simulate how the robot is supposed to learn in real life. So every time, they can't really learn like the supervised learning manner. If we consider the robots to become part of our lives, we should sort of expect them to learn like humans. So we keep learning throughout our life. So it's not like we have a single or a number of data sets predefined in advance, and then we train our model on this, and that's it, the static model. Instead, the robots are supposed to learn as it goes as well. So we wanted to do some continual learning experiments with Bayesian neural networks. And here we plot the loss. So we actually approach each of the actions that I presented, the 16 actions, as different tasks. So you see basically the loss on each action as root mean square error between the predicted appropriateness, and when the model is trained on that task or action, the loss drops for that action and it stays low throughout the continual learning process, meaning that the model actually is able to mitigate for catastrophic forgetting. So does not really forget the previous knowledge. And we found that the average root mean square error for all of these actions is 0.63 on the test set, which we found as satisfactory because we have a scale, remember, from 1 to 5. So here are some representative results. Again, taking that extreme scene where the robot is alone, we see actually, so we have variations of Bayesian neural networks where we can also do two-class or two-task learning if we divide the 8 actions around the circle or within the direction of the arrow as separate, or if we want to learn all 16. So we see actually how the results are. In general, what we can say is that the models are able to learn actually quite close to the actual labels for different actions, as is indicated by various numbers we have there. Here's another example where you have more people. And again, we can see, for instance, now, there are people, so vacuum cleaning becomes actually less appropriate, and the models again are able to predict that. And things like, carrying food is more appropriate, or carrying drinks. And this again is predicted by the models as well. In terms of conclusion or future work, here we actually looked at third vision perspective. So here I'm just exemplifying it with the NASA's Mars rover. So this is like from third vision perspective, how the world would be seen. But actually what's important is for the robot first person view, for the robot themselves, and how they should see the world from their own eyes, which is quite different. And one limitation of that data set is it is actually third person perspective. So it would be good to focus and create some data sets like that from robots' first person perspective. Then the last thing I want to mention briefly as a sneak peek, because this is actually going to be presented at HRI 2022 in March. So we just had the paper acceptance. In a way, it combines some of these aspects that I presented with the first work on taste, liking, and facilitation. And the second part is appropriateness. And the work is called Learning Socially Appropriate Robo-Waiter Behaviors Through Real-Time User Feedback. So I'll just briefly mention, we made actually a custom-made simulated data set to learn appropriate positioning and movement behaviors for a robot waiter. And again, we use crowdsourcing labels to pre-train a reinforcement learning agent. And the idea was then to actually empower the humanoid service robots with interactive learning. So we wanted the robot to learn on the fly and adapt from social feedback with implicit and explicit rewards. And this is how sort of it looked I won't be saying more. So hopefully, perhaps you can attend HRI 2022 and see our work there. And with this, I'll conclude. So if you're interested in some of these topics, we have had multiple research topics in frontiers in robotics and AI. So one is called Effective and Social Signals for Human-Robot Interaction, which was also nominated for the Frontier Spotlight Award. Then we also organized workshops at Roman and HRI on lifelong learning. So the videos of the talks are available. And this year at HRI 21, we also had lifelong learning and personalization. In long-term human-robot interaction, again, you can access the videos. And we have the research topic also is already live with all the articles available on lifelong learning and long-term HRI. And finally, I would like to thank my group and the funders. And I'm ready for your questions. Thank you.